A Watermark for Large Language Models, a paper written by researchers from the University of Maryland. Before we begin, this presentation was prepared for the Build 597 seminar course at Tobeto. About this paper was first published on arXiv on January 24th, 2023. It was accepted at ICML 2023, where it won the Outstanding Paper Award. The latest version of this paper was published on May 1st, 2024, which is quite recent, and this paper has been cited over 350 times since its publication. Abstract. This paper proposes embedding a signal, i.e. watermarking, into token distributions when generating text using large language models. The embedded signal can be detected after the text is generated, thus proving that the text was produced by an artificial process. This study examines, obviously, their method of embedding this signal during text generation, the statistical analysis of detecting the said embedded signal, and how embedding this signal affects the model's text generation capability. Why watermark? Why should we watermark? Well, large language models have gotten really good lately, so much so that it is really hard to distinguish human-generated text, or as I will call it, natural text, from artificially generated text. They pose a certain risk of misuse, some inconsequential stuff like plagiarism, and some consequential stuff like misinformation and like generating personalized hate speech to change a outcome of like an election or whatnot. So they can have some serious risks. Watermarking can help identify artificially generated text and mitigate potential risks. What we are trying to achieve with watermarking is to be able to confidently say that a passage is machine generated. We want the text to be traceable. We want to trace the text back to the model that generated it. What is watermarking? Well, watermarking, as defined in this paper, is a concealed pattern within text that is invisible to the human eye but can be algorithmically identified, serving to determine whether the text is synthetic or not. A watermark should be detectable algorithmically without access to the model parameters or the language API, should be usable on a standard language model without modifying the model parameters, so no fine-tuning. Should be detectable from a contiguous portion of the generated text, we should not be able to remove without altering a significant portion of the generated tokens, and a watermark should have a statistically provable detection method. Before we begin our study of watermarking, we should talk about some notation and some language modeling basics. Language models are working in the realm of tokens. Tokens are sometimes words or word fragments, and the model can interact with a finite tokens. So the number of different tokens that a model can accept changes between 16,000 to 256,000. So like when you ask ChatGPT a question like how many R's are there in strawberry, first we tokenize that. So it is tokenized to this. Every single token has a unique token ID, so the model only interacts with this token ID. If you are careful, you can see that ChatGPT actually answered this incorrectly. It claimed that strawberry contains 2 R's when in fact it contains 3 R's, because ChatGPT does not have the information for every single character it was given. It only is working in the realm of tokens. This is a core limitation of the current language modeling schemas. A token sequence is a sequence of tokens, and what the language model does is, using the previous tokens, it generates a new token and appends it to the existing tokens. How does it do that? Well, a language model produces a probability distribution vector over the vocabulary, and using this distribution, we sample from this distribution a token, and we accept that token to be the next token. Why do we sample? Why don't we just take the token with the highest probability? Well, that has some side effects that I will not be going into for this presentation. for now, we should know that when the language model produces the probability distribution, we just sample from that distribution to pick the next token. The difficulty of watermarking low entropy sequences. The core limitation of watermarking is watermarking low entropy sequences. I will be mentioning this again and again and again, so I wanted to mention it first and get it out of the way. What is a low entropy sequence? It's a predictable sequence, making detection very difficult. If you ask ChatGPT to recite the Constitution of United States, it does so in a perfect manner. It has memorized this text because it probably exists many times in its training data. So sometimes when you ask the model certain questions, it will just regurgitate the existing information that it memorized. So it will just retype the originally human text back to you. This is impossible to detect as watermarked, even though it is from a language model, because it originally is human generated text. Yeah. A proof of concept. So in this paper, they propose two different algorithms, one hard watermarking and one soft watermarking. Soft watermarking is a slightly more nuanced way to watermark. Hard watermarking, we need to understand to be able to understand the more nuanced algorithm. So this is the hard watermarking algorithm. So we have a prompt, a token sequence, and for every single token we are generating, we will apply the language model to the prior tokens to get a probability vector over the vocabulary for the next token. We compute a hash of the previous token and use that hash to see the random number generator. Using this random number generator, we randomly partition the vocabulary into a green list and a red list of equal size. When sampling the next token, we choose from the green list and we never choose from the red list. To demonstrate this, I prepared a graph. So normally we have a prompt. The prompt is I have A, and we want the model to generate the next token. The model produces a probability distribution over the vocabulary. So the token for pencil has some high probability, car some less, and bicycle some less. And we sample from this distribution. Let's say for this example we sampled pencil. We append this token to the end of the text. Right now the text we have at hand is I have a pencil, and we can generate more tokens from this. Well, how does hard watermarking work? Again, we have the same prompt. I have a the model produces the exact same probability distribution, but on the side, what we do is we use the last available token to hash the hash of that token to seed a PRNG, a random number generator. Using this random number generator, we randomly partition the vocabulary into a green list and a red list, and when sampling, we only sample from the green list. Let's say we have a candidate passage as we have right here, and we would like to determine if it's generated using this hard watermarking or not. So what do is we need to determine which list every single token is coming from. So let's take this token, candidate. Is candidate from the green list or the red list? Well, how do we know? We need the partition of the vocabulary to determine which list this token comes from. Well, how do we get the this partition? Well, we need the previous token. Do we have the previous token at hand? Yes, we have the candidate passage, so we have the previous token. Using this token A, we again use the hash of this token to seed a random number generator, which produces the exact same partition of the vocabulary as in the generation, so we can easily determine if this token is in the green list or the red list. So if the hard watermarking was used during generation, every single token generated must be from the green list. If a significant portion of the tokens are from the green list, we can confidently claim that this text, this candidate passage, is watermarked. Because when we are talking, generating natural text or non-watermarked text, we don't care for this green list partition. So if a text is not watermarked, the expected number of green tokens is half of the tokens. But if text is watermarked, then we expect the majority of the tokens, in this case all of the tokens, to be green, from the green list. Producing watermark text obviously requires access to the language model, but detection does not. A third party with the hash function and a random number generator can recreate the red-green list partition for each token and count the violations. Because the red list is chosen at random, a human written passage or non-watermark text is expected to violate the red list rule with half of their tokens, while the watermarked model produces no violations. The probability that a natural source produces t tokens without violating the red list rule is only 1 over t to the t power, 2 to the t power, which is vanishingly small. To evaluate this, we need a null hypothesis, which is that the text sequence is generated with no knowledge of the red list rule, and if we are successful in rejecting this hypothesis, then we can declare the candidate passage at hand to be watermarked. To robustly detect this, we need a z-score test. If h0 is true, the number of green list tokens, so if the text is not watermarked and the text is of length t, t tokens, the expected number of green tokens are t divided by 2, and the variance is t divided by 4, because every single token is a Bernoulli trial. So here is the z statistic. So we have the number of green tokens in the candidate passage divided by the expected number of green tokens in that passage, which is divided by the square root of the variance of the number of green tokens, which gives us how many standard deviations are we away from a non-watermarked text. We reject h0 if z is above a chosen threshold, which in this paper they set as 4. If z being more than 4 means the probability of a false positive is 3 times 10 to the minus 5. How did we get that number? We get this number from the normal distribution table. If the probability of something being away from the mean 4 times as the standard deviation is very, very low. With this paradigm, we can detect any watermark sequence with bigger than that has more than 16 tokens. Well, why 16? Because 16 is the lowest number that can achieve a z-score of 4. How hard is it to remove the watermark? Let's say we have watermarked text and we want to remove the watermark. Let's say we change a single token. Originally this token was in the green list, but let's say we change it to a red list token, so that produces a single violation. Since this token was used to generate the red-green list partition for the next token, we can at most produce 2 violations if we change a single token. So let's say we have a sequence of 1000. If an adversary changes 200 tokens, we can create up to 400 violations. Even with these changes, 600 tokens are still on the green list and watermark still remains detectable. So you need to change the vast majority of the text for the watermark to be not detected, which makes sense, because if the majority of the text is changed, it no longer is machine generated, is it? Drawbacks of this hard red list rule. The hard red list rule handles low entropy sequences in a simple way. It does not. It prevents the language model from producing them. For example, the token Barack is almost deterministically followed by Obama in many text datasets, yet Obama may be disallowed by the red list. So, if the model is generating after Barack, it will most likely choose Obama. The probability distribution will be completely concentrated around the token for Obama. But if the token Barack produces a green red list partition in which the token for Obama falls in the red list partition, then Obama is disallowed to be chosen. So this watermarking scheme just disallows some bigrams from being generated, which degrades the quality of the text. We can get around this, but there are some tricks we can do to get around this phenomenon, but there is a slightly more sophisticated algorithm called soft watermark, which supposedly removes these limitations. In the soft watermark, the general idea is on the hard watermark, we are doing the green-red list partition and blocking the red tokens from being generated. In the soft watermark, we are not blocking the red tokens from being generated. We are only slightly promoting the green list tokens. Since we are promoting green list tokens, we expect more green tokens to be chosen at the end. Yeah. So in this matter, if a token is in the red list, but it captured a lot of the probability distribution, it can still be chosen. Yeah. Derivation of soft watermark. I said that a language model produces a probability vector over the vocabulary. Well, I lied. A language model actually produces a vector of logits, and you use the softmax function to convert these logits to a probability vector. What we do is we add a constant theta to the logits of the green list tokens. So here is the algorithm for soft watermarking. First of all, the green list's size is now a hyperparameter between 0 and 1. In the hard watermarking, it was set to be 1/2. And the hardness parameter, the promotion factor, is also a hyperparameter. For every single token we are generating, we apply the language model over the prior tokens to get a logit vector. We compute the hash of the previous token and use that hash to seed a random number generator. We randomly partition the vocabulary into a green list and a red list, so this is all the same. Now, these logits, we are adding a constant factor to the green list logits, which shifts the probability mass from the red list tokens to the green list tokens. So there is a bias towards the model to pick a green token. We sample the next token using this watermark distribution. Again, I have an excellent diagram of this. The left part is exactly the same. We use the previous token to previous token's hash to seed a PRNG and use this PRNG to partition the vocabulary to a green and red list. So we have red list tokens, we have green list tokens. What we do is we just add a little bit to the logits of the green list partitions, and we don't touch the red list tokens. The green list tokens, we just add a slight bit more to the logit. Then when we softmax this value, the probability mass is shifted slightly towards the green list tokens. Here is the softmax function. As you can see, there is a constant added to the token if it's from the green list, and it's left alone if it's in the red list. This has quite a nice property of adaptive enforcement of the watermark. We just ignore the watermark rule in low entropy cases, and high likely words still remains the high likely words, even though if it's in the red list. Yeah. The detection process is identical to the hard watermark. We just count the number of green tokens, and if we have a substantial number of green tokens, then we can conclude that the text is watermarked. Here is the generalized z-score. Again, the same z-score threshold. Again, yeah. So let's do some sensitivity analysis of this watermark. If we have high entropy sequences, we will always generate green tokens, but if we have low entropy sequences, then we will require more and more tokens for detection. They define a spike entropy, which defines the entropy of a distribution, and given this spike entropy, they can give an estimated number of green tokens in a candidate text. This has a really long proof, but I will not be going into that. Again, really smart guys, they also derived a variance for the number of green tokens given a spike entropy value. This is a really massive formula, but if you enter the constants, it gets quite simple. The type 2 error analysis. Here is an experiment. We are generating 200 tokens. So the average spike entropy per sample was 0.8. The expected number of green tokens was to be greater than 142, assuming this spike entropy. The empirical average was 160. So from the 200 tokens generated, 160 of them were from the green list. The sensitivity was estimated to be 98.6, again assuming this spike entropy. The empirical mean the 159 green tokens, which makes the type 2 error rate to be 5.3 times 10 to the minus 7, so very low. Empirical results show that 98.4% of the generations were detected. 99.6% of the generations were detected if the distributions were decoded using four-way beam search. For beam search is a different way of decoding, so it's not simply sampling a token from the distribution, but I will not be going into this. If I do, the presentation takes a really long time. And we have a 100% detection rate for sequences with spike entropy above the 25th percentile. So if you have enough entropy, the watermarking is quite successful. The failure cases are low entropy sequences with typically involve data memorization, and in my experience, failure cases often look like some repetitive text. Handling repetitive engrams, if like in a text, New York, let's say, both New and York are in the green list, and if New York is mentioned over and over again, that can artificially inflate the green token count. There are some possible remedies to that, which I will not be getting into. Soft watermarking and perplexity. So how this soft watermarking affects perplexity. If the entropy is of maximal entropy, if the distribution is of maximal entropy, so every single token has the same probability, then the randomness is not unchanged too, so the perplexity is unchanged by watermarking. If the distribution is of minimal entropy, so the distribution is focused around a single token, the soft watermark rule has really no significant effect, because the probability mass still is going to be concentrated around that single token, even if some green list tokens are promoted. Impact on moderate entropy tokens. So the watermarking only impacts the moderate entropy tokens. We can give an expected perplexity, but again, I will not be going over too deep for this because it takes a long time. Here are some experiments. The experiment setup is as such. The watermark strength will be measured with the z-score I mentioned, and the text quality is going to be measured using perplexity, using an oracle model, so a bigger model. Perplexity, lower perplexity means more likely better text for our purposes, and high perplexity means unlikely bad text. So there is a trade-off between the detectability of the watermark and the quality of the text, obviously. So on the left, as you can see, we have different promotion factors and different partitions for the green list, red list. If the promotion factor is 0, then we are essentially not watermarking, so the z-score is also 0. As the hardness of the watermark increases, it's more detectable, but the quality decreases. So this promotion factor produces an outrageous z-score of 40, which is very highly detectable, but it degrades the quality quite a bit. On the left, there is a very similar graphic, but using the beam search decoding. Again, I will not be going into that. Yeah. As the text gets longer, so as we have more and more tokens at end, the z-score increases, so we are more confident in our conclusion. Yeah. Here is the detection accuracy, so no type 1 errors and very low type 2 errors, again attributed to low entropy text. Yeah. In conclusion, from these experiments, the proposed watermarking method is quite effective for detecting machine-generated text while degrading the quality in a minimal manner. Attacking the watermark. So, let's say we have watermarked text at hand. We want to attack it so that we remove the watermark. The attacker aims to create a watermark-free text using a private watermarked model and potentially a weaker public model. There are a few different attack types, mainly text insertion, deletion, or substitution. For example, paraphrasing attacks. You can paraphrase manually, which requires human intervention, which is costly. You can use automated paraphrasing using paraphrasing models, which uses a public language model to rephrase the watermark text. But there is a crucial trade-off here, which is that the attacker will use a weaker model to paraphrase, because if the attacker has access to a stronger non-watermarked model, then why not just use that model, you know? So again, this paraphrasing will definitely reduce the quality, and watermark will only be weakened and may still be detected. There are some other attacks, such as like adding white spaces or misspellings, which can be mitigated by normalization. Tokenization attacks, modifying the text, the mess with the tokenization. Also homoglyph and zero width attacks also mess with the tokenization, which can also be mitigated by canonicalization. Generative attacks, you can exploit in-context learning to manipulate output in a predictable and reversible way, an example being the emoji attack. This is the most effective way to attack the watermark. So let's say ChatGPT is a watermarked model, and I ask it something, and I also ask it to replace spaces with smiley face emojis. So the model returns some text, like here, so, and every single space has been changed with a smiley face. Right now I have the text I want at hand. Only thing I need to do is removing this smiley heads. This breaks the watermark because it breaks the property that we want. We need continuous text. If we remove these tokens, since this token was used to generate the green red list partition, when we remove this token, we will look at the token for the to generate the green list partition, which obviously was not used during generation, so this will definitely break the watermark. But there is a certain problem with this. First of all, these all smiley faces will definitely manipulate the attention weights, the aggregate attention weights. Also, they are eating the valuable context size, which is the number of tokens the model can handle at once. As a defense, you can just include negative examples. Like if you ask the model for instructions to build a pipe bomb, it will not answer, so you can just disregard such prompts using fine-tuning or RLHF. There's a span replacement attack, which replaces a single token using a generative process. So we get the text, we tokenize the text, we change some tokens with mask tokens, and we use the T5 large model to replace these mask tokens with new tokens. The attacker operates under a word replacement budget to maintain a semantic similarity. So the more and more you replace, the semantic similarity deviates from the original text. From this graphic, you can see that as you attack it more, the watermark is less detected, but the perplexity also gets quite larger, and the most importantly, the watermark degrades gracefully. So when you remove a single token, the watermark just does not disappear. As you attack it more, the watermark degrades more. In conclusion of this experiments, the watermark is easily verifiable, statistically improvable for false positives, degrades gracefully when under attack, can be easily retrofitted to existing models, and it can be deployed in a context-specific manner, which I think is a very important property. You can just turn off the watermarking because it is all done in the sampling stage. When a user is behaving in a suspicious manner, you can just turn on the watermarking when that happens, and you can turn it off when you are not suspecting. Some open questions: hashing rules. We need some analysis of that, and watermarking definitely affects the factuality of the model. Some limitations. Some various decoding parameters were just completely unexplored in this paper, so no top K, top P, temperature, which directly affects the entropy of the output distributions. They were just disregarded. In final conclusion, this watermarking scheme offers a practical solution. The proposed watermark is robust, efficient, and quite flexible. Okay, some boring related work. Watermarking is a field with a long history, so it's called steganography. So we have text at hand, and we want to hide information in this text for a secret message. So watermarking is obviously much easier for continuous valued data, so information hiding, yeah. Some early approaches are just rules based, change some tokens to detect a watermark or whatnot. Modern neural language models such as transformers and BERT enabled some new and improved steganography or watermarking ways. Kapchuk et al. Notably proposed Meteor, a cryptographic steganography framework using generative models. So if the sender and receiver has a shared model, they can send messages safely. Watermarking model parameters, you can directly embed the watermark into the model parameters, but then you cannot turn it off. They have some different implications. Post-hoc detection, you can just try to detect the watermark after the fact, non-watermarked text. So ChatGPT produces text in a certain manner, right? In chapters or whatnot. So using the machine-generated text and just trying to detect that using its inherent properties. The effectiveness of these methods decrease as the LM capabilities increase, and they are quite vulnerable to adversarial attacks, and sadly there is some potential for false positives, especially for non-native speakers. So watermarking is definitely much more robust and secure than these approaches. Finally, some acknowledgements. This paper was made possible by the ONR MURI program, DARPA GUARD, the Office of Naval Research, and the AFOSR MURI program. Commercial support was provided by the Capital One Bank, the Amazon Research Award Program, and Open Philanthropy. Further support was provided by the National Science Foundation and the NSF Trials Institute. And to the left we have two pictures of Mr. Richie Rich. Okay, thank you for listening to me. Have a nice day.